At this point in the homework, you should have an appreciation for the differences between an SN2 reaction and an SN1 reaction. How, for example, you could get different products from them. An SN2 reaction gives you only inversion of configuration at a chiral center, whereas an SN1 reaction gives you a racemic mixture, a 50-50 mixture of the two enantiomers. Or, in an SN1 reaction, you might have a carbocation rearrangement, so the nucleophile attacks a different position. And also, you mix different types of reagents with the two reactions. So, you can speed up the reactions in different ways based on either with the concentration of the substrate or the nucleophile, or both, depending on the mechanism. So there are a lot of differences between SN1 and SN2 reactions, and they're both really, really common. Now, up until this point in the homework, each of the exercises have told you this reaction is an SN1 reaction, or this reaction is an SN2 reaction. Given that information, do the following. But now, starting with exercise 726, they're going to try to just give you the reagents, and you have to figure out, will this react in an SN1 reaction or an SN2 reaction? And really, the clearest way to do that is to look at the carbon that the leaving group is on. In the video on understanding substitution reactions, we developed this little table. We talked about everything here, and we said that SN2 reactions happen best when the leaving group is on a primary carbon, because then there's no crowding, the nucleophile has plenty of room to come in and attack the electrophile. And they happen worst when the leaving group is on a tertiary carbon, because then everything's really crowded and the nucleophile can't get to the electrophile. So, on the other hand, we discussed how, because an SN1 reaction creates a carbocation wherever the leaving group is, if the leaving group is on a primary carbon, you would try to be forming a carbocation on a primary carbon, a primary carbocation, which is very unstable, so that disfavors the SN1 reaction. And if the leaving group is on a tertiary carbon, then you'll form a tertiary carbocation, which is the most stable. And in the case of SN1 reactions, crowding doesn't matter, because after the leaving group leaves, the molecule is trigonal planar. The carbocations are all bonded to 3 atoms and have 0 lone pairs. So they're trigonal planar, which means they're flat, and so the nucleophile can attack it like a pancake, either on the top or on the bottom. In other words, the big takeaway from this is, if the leaving group is on a primary carbon, it will definitely happen through an SN2 reaction. If the leaving group is on a tertiary carbon, it will definitely happen through an SN1 reaction. The only time there's ambiguity, the only time it's kind of vague, is if the leaving group is on a secondary carbon. If the leaving group is on a secondary carbon, it could be either SN2 or SN1. You'd have to look at other factors that we'll cover in future videos. But for right now, we just want to assess, just looking at the crowding of the carbon that the leaving group is on, can you tell whether the reaction will be SN2, SN1, both, or neither? The neither is an interesting case. It's just that the leaving group has to be on an sp3 hybridized carbon. If the carbon has any type of a double bond on it, then this reaction won't happen. You won't get the substitution reaction. So that's the only time where you would have neither. Okay, so we'll look at this. The leaving group is the bromine. It's on this carbon here. That's bonded to 1, 2, 3 other carbons. So that's tertiary. Tertiary favors an SN1 reaction. So we know that that would happen through an SN1 mechanism. If we go through the same thing for B, our leaving group is chlorine. It's on this carbon. This is bonded to just one other carbon, so that's primary. And if the leaving group is on a primary carbon, that favors an SN2 reaction. Here we have the leaving group on a carbon in a double bond, and we said that disfavors substitution, so that would have neither SN1 nor SN2 happening. Here, this is the carbon that has the leaving group on it. It's bonded to 1, 2, 3 other carbons, so that's tertiary. If the leaving group is on a tertiary carbon, that favors an SN1 reaction. Here we have a leaving group, and I think there was a typo here. So if in your homework there's not an iodine there, make sure you write an iodine. The iodine is your leaving group. If that's that carbon, that iodine is bonded to this carbon here, that carbon is bonded to only one other carbon. So it's primary, and having the leaving group on a primary carbon favors an SN2 reaction. And again, if it's not clear why a primary carbon favors SN2 and a tertiary carbon favors SN1, I encourage you to go back to that video titled Understanding Substitution Reactions, where we fleshed out this table. So now we'll go down here. For these last two, you see that the bromine is on this carbon. This carbon, though, is involved in a double bond, and that was the neither case. So that won't work. So neither SN1 nor SN2, you wouldn't get a substitution reaction there. Here the bromine is on this carbon. That carbon is just bonded to one other carbon, so it's primary. And if the leaving group is on a primary carbon, that favors SN2. So the big thing to remember from this problem is if the leaving group is on a primary carbon, it'll be SN2. If it's on a tertiary carbon, it'll be SN1. If it's on a secondary carbon, it'll be both. And if it's on a carbon that is involved in a double bond, then it'll be